Hi, my name is Lukas Ulrich and I am an environmental engineer. I work at the department Sandek at EAWAG in the research group on strategic environmental sanitation planning. In this module, we will start looking at the different technologies which can be used to design a sanitation system. We will go through the technologies functional group by functional group, from the user interface to final disposal or end use. In this course, we cannot cover all technologies in detail, but we will give a brief introduction to most of them. If you would like to learn more about a specific technology, I recommend you to read the corresponding section in the Compendium of Sanitation Systems and Technologies. The compendium provides a double-page description with further explanations for 54 different technologies. So, let's get started with the first functional group, the user interface. The user interface describes the type of toilet, pedestal, pan or urinal with which the user interacts. It is the way by which the user accesses the sanitation system. The user interface must guarantee that human excreta is hygienically separated from human contact to prevent exposure to fecal contamination. In this module, you will get to know which different user interface technologies there are and how they function. You will learn which input products they can deal with and which output products they generate. You will also find out what needs to be considered to choose and design a user interface for a specific context. So, let's take a look where our friends pee and poo can go. The oldest and most widespread user interface option is the dry toilet. In its simplest form, it consists of a slab with a drop hole and possibly footrests to provide some user guidance. This design is suitable for those who prefer to squat. For users who prefer sitting on a toilet, a pedestal can be installed. Let's take a look at the products which can go into a dry toilet and what comes out of it. Obviously, feces and urine go into the toilet. Anal cleansing water and dry cleansing materials can also possibly be input products. However, they do not always occur, and for some subsequent technologies, it is not recommended to put them into the toilet. This is indicated by the gray font and the dashed lines. Whether anal cleansing water or dry cleansing materials occur or not, of course depends on the user preferences. As you can see on this diagram, flush water is not listed among the inputs. That is why we call it the dry toilet. When urine and feces are mixed, they are called excreta. This is the principal output product of a dry toilet. Depending on the local context, anal cleansing water and dry cleansing materials may be mixed into it, indicated by the plus. This way of structuring the input and output products of a user interface may seem unnecessarily complex, but when we design a sanitation system, it allows us to select a compatible technology which can follow. In this case, the subsequent technology should be able to deal with excreta as an input product. In these photos, a few different dry toilet designs are shown. You can see that different materials can be used, from wood, which may be a bit difficult to clean, to concrete and prefabricated plastic. Also, the drop hole can take different shapes. The keyhole design, for example, is a very common one. A round slab has the advantage that it can be rolled. For example, to move it to a new pit, when the old one is full. A lid may provide a certain barrier against odors and flies, but is not always recommended, especially for subsequent collection technologies which need to be ventilated. Now let's look at another type of dry toilet, the urine-diverting dry toilet or UDDT. This option allows to separately collect urine and feces. The one I have here is a plastic model from China. It has a lid which a user can open with one foot and close again. The special thing about this user interface technology is that it has kind of a funnel in the front where our friend P can go. For our other friend, Poo, there is the drop hole at the back where he just can jump in. This technology option is of particular interest for those who want to use the normally sterile and nutrient-rich urine as a fertilizer in agriculture. A urine-diverting dry toilet can be designed in various ways to suit the preferences of almost all users. It can be a squat model, as the one from China I showed, or it can be a pedestal to sit on. For those who use water to cleanse rather than dry cleansing materials, designs exist which have a separate bowl for the collection of anal cleansing water. The input products of a urine-diverting dry toilet are exactly the same as for the regular dry toilets. The difference can be seen in the output product, where pee and poo stay separate and do not form excreta together. Depending on the dry cleansing materials used and the subsequent collection technology, dry cleansing materials may go into the drop hole with the feces. Anal cleansing water is never mixed with feces because they should always stay dry. Where anal cleansing water is used, it should always be collected in a separate compartment of the toilet and disposed of separately. These pictures show a wide range of different urine-diverting dry toilets, with squatting models above and sitting models below. Urine-diverting dry toilets can be made of ceramics, concrete, or plastics. They can even be self-made using a funnel and a bucket, as shown in this image here. Where men prefer to stand for urination rather than sitting or squatting, it can be a good idea to install a urinal to collect their urine. Urinals also exist in different designs, and they can be water-flushed or waterless. Inputs include urine, and in case of flush models, also flush water. Depending on the design, urine emanates in undiluted form or diluted with flush water. Especially where the urine is collected in a tank and where it is supposed to be used as a fertilizer, it is recommended to collect it without dilution to reduce the volume. Urinals can take a variety of shapes and are usually made of materials like plastics or ceramics. All the urinals shown here are waterless ones, except this one here, which has later on been retrofitted to be waterless by closing all the holes in the drain except one to limit the odor emissions. Waterless urinals should always be fitted with an odor seal, such as the rubber one shown in this picture. There are also designs for women, but they are not widely available and implemented. Those two here on the right side are female designs. The next technology is the pour flush toilet. It has its name from the bucket that is used to pour water into the bowl to flush it. Pour flush toilets should be equipped with a U-bend, also called S-trap, or gooseneck, which acts as a water seal. This seal effectively prevents odors or insects from returning to the user interface. In addition to the input products that we already had for the dry toilet options, the pour flush toilet depends on a source of flush water to function. The product that comes out of the user interface is the mix of excreta, flush water, and possibly anal cleansing water or dry cleansing materials, called black water. Pour flush toilets are mostly made of ceramics and typically in the squatting design. Pour flush sitting toilets have also been developed, but they are not widely available and implemented. The cistern flush toilet, or water closet, is another very widespread and well-known water-based user interface. It also has a water seal and is equipped with a water-filled cistern. When the user operates the flush mechanism, the water from the cistern is released into the toilet bowl to carry away the excreta to the next functional group. Both sitting and squatting models exist. The input and output products of a cistern flush toilet are exactly the same as those previously shown for the pour flush technology. Black water is also generated as an output, but normally in larger quantities than in the pour flush toilet due to the higher water use. Cistern flush toilets exist since more than 2 centuries, but only became a popular industrial product in the late 19th century with its worldwide spread starting from Europe. As you can see on the right-hand side, flush toilets looked quite different in the beginning from how we know them today. The urine diversion principle has also been applied to the cistern flush toilet, as urine-diverting flush toilets were developed in more recent years. This user interface technology is equipped with a bowl for the collection of urine and with a water seal through which the feces are carried away. There are designs with valves which close during the flush to collect undiluted urine. Other designs do not prevent a small quantity of flush water from entering the urine pipe. The urine-diverting flush toilet has again the same inputs as a pour flush system or a cistern flush toilet: feces, urine, flush water, anal cleansing water, and dry cleansing materials. However, the urine is not mixed with the other products, but separately collected. The resulting urine-free product, which is flushed away, is therefore called brown water. This technology also exists in different shapes and colors, and as sit and squat models. This design here is also installed at the EAWAG offices. It collects urine, which we use for our research, mainly to study ways how to recover nutrients for the production of fertilizers. The blue diversion toilet, which was developed by EAWAG in collaboration with industrial designers from EOS in Austria, is a special variant of the urine-diverting flush toilet. It also has a flush, but only to clean the urine collection bowl, as you can see here in the image. The water is then treated and recycled. Feces and urine, they are not mixed with flush water. Therefore, this design does not generate brown water as an output. Urine-diverting flush toilets are not very widespread yet because of some design challenges, high cost, and limited demand. We now have seen 6 different options for the user interface. But how can we choose the right one for a given context? There are a number of factors on which the technology choice depends. The availability of water is crucial for all technologies which depend on flush water to carry away the excreta. The user interface should of course also take into account the preferences and habits of the people who use it. Are they sitters or squatters? Washers or wipers? Another important factor is the local availability. Can I find the technology on the local market, or can I build it myself? As we have seen, the different technologies generate different output products with very different characteristics. This influences the technology which can come next, be it a collection and storage technology or a conveyance technology. Last but not least, special needs of user groups should also be considered, such as the needs of children, elderly, or disabled. People's needs change based on age, location, health, physical ability, mental state, etc. The concept of inclusive design takes this into consideration. Inclusive design aims to remove barriers that exclude people from being able to use facilities as a result of their evolving needs. It ensures equitable access for all, including marginalized user groups, which may in some cases also face some barriers and exclusion from sanitation and hygiene facilities. An example of inclusive design is the provision of ramps or the installation of handrails in toilets to ensure easy access. Inclusive design considerations are of particular importance for facilities at schools or health centers and for public toilets. In the last few minutes, we have gone through a variety of designs through which people access a sanitation system. To sum it all up, I would like to highlight 4 key points. Different designs have been developed for different user preferences and habits, such as squatting and sitting toilets, as well as options which allow the use of different materials for cleansing, such as water for washing or dry materials for cleansing. Second, there are 2 main types of interfaces: dry technologies that operate without water and water-based technologies that need a regular supply of water to properly function. Third, different user interface technologies generate different output products. This, of course, influences the subsequent type of collection and storage technology or conveyance that is possible. Finally, the design should not only consider technical aspects and user preferences, but also the barrier-free access for all users. In the next modules, we will be looking at the following functional group: collection and storage, and on-site treatment. The following modules will also answer the question of this fellow here. Where do the products generated at the user interface go? See you later.